In our previous video, we went through the entire process of conducting a one-sample z-test, in which we thought that our math intervention would lead to higher SAT scores. Now, let's see what happens if we keep everything about the example exactly the same, but all we do is increase our sample size from 16 to 64. Mu naught, the hypotheses, sigma, our sample average, all stay the same. All we're going to do is increase our sample size from 16 to 64. First, and we'll see the most important thing, is that the standard error is now smaller. Instead of 100 divided by the square root of 16, it's now 100 divided by the square root of 64. The standard error is cut in half from 25 to 12.5. If we first look at the distribution of means when we had a sample of 16, we see that by increasing the sample size to 64, the spread for our distribution of the means becomes much more compact. Also, notice that as the distribution got more compact due to the standard error becoming smaller, our z-scores also change and become more compact because they're based on the standard error. Now, our critical z-score will still be 1.64. 5% of the time, we would randomly expect to get a sample with a mean of a z-score equal to 1.64 or more. So we can flag the point where z equals 1.64 and use that for our critical score that must be exceeded to reject the null. It's the border to our region of rejection. The difference is that now with the distribution more compact, the SAT score associated with that critical z-score of 1.64 is going to be a lot closer to 500. A little quick math using our critical score formula, and we see that the critical score, the mean SAT score we need to reject the null hypothesis, is now only 520.5. A sample of 64 students only needs a mean greater than 520.5 in order to reject the null. That's because with a larger sample, there's more opportunity for extreme scores to cancel out. So it's less likely that we'll just randomly see very high or very low sample means. As a result, look what's happened. Now our sample mean of 530 is clearly in the rejection region. By increasing the sample size, we're able to reject the null hypothesis even if the sample mean doesn't change. Finally, there's the question of the p-value. Conceptually, this is very important. With a sample of 64, just how often would we have randomly ended up with a sample mean that was 530 or greater? With a smaller standard error of only 12.5, our z-score is now equal to 530 minus 500 divided by 12.5 instead of 25. So even though our sample mean hasn't changed, our z-score is now 2.40. Our p-value is equal to the area for a z-score of 2.40 or more, or a mean SAT score of 530 or greater. This is the blue shaded area in our figure. As you can see, it's pretty small and in fact a little hard to see. Based on the normal curve, we can easily check and find that the area for a z-score of 2.4 or more is equal to 0.0082 or only 0.82%. We would have only expected to randomly see a z-score of 2.40 or more 0.82% of the time. In other words, if the null hypothesis were true and the average for the population of students who might receive the intervention is in fact 500 or less than 1% of the time well, 0.82% of the time, we would have randomly ended up with a sample of 64 students whose mean score was 530 or greater. That's not very likely if the null hypothesis is true, so maybe the mean for the population of students who receive our intervention is not 500 or less. We reject the null hypothesis. So, wrapping up our summary of the problem, we can now say that our z-score was equal to 2.40. This corresponds to a p-value of 0.0082, which now is less than our alpha level, and so we are able to reject the null hypothesis. Again, nothing has changed other than we increased our sample size. But now the mean of 530 is statistically more extreme, and we're able to reject the null. So that concludes our video. In the next video, we'll work through a problem with non-directional or two-tailed hypotheses. Then in the final video in this series, we'll discuss confidence intervals and how to calculate one for our estimated mean. Bye for now.